Hi guys, in this session I'm going to deal induction machines crash. Okay, with this induction machine analysis you will be able to solve all 100% of the old gate questions and at least 90% of the upcoming gate exam also you will be able to solve. Okay, and before entering into induction machine, let me tell you one thing. Basically machines is easy provided you have to understand the heart of the machine. Okay, the crux of each and every machine will be there. You should be able to understand that. Once you understand that, remaining is a simple cakewalk. Okay, for example, in induction machine means the crux or heart of induction machine is rotor circuit analysis. Okay, anyway, I'm going to start from basics. Okay, speed control, starters, braking, okay, everything we are going to cover, including harmonics also, and I will try to complete it within 1.5 hours. Maybe some extension can be expected, but within 1.5 hours I'm planning to complete this particular lecture. With this lecture, at least you will be able to solve 90% of the upcoming gate exam questions in induction machine. Okay, and let me start with basics. Okay, basics, first thing is, in order to have continuous electromagnetic torque, okay, continuous electromagnetic torque is required either as a motor or a generator. Okay, means for a motor also torque is required, for a generator also torque is required, because either generator or motor, one side of the machine mechanical power should be there. Okay, we know that motor will deliver mechanical power and generator will absorb mechanical power. Somehow mechanical power involvement should be there. Okay, the moment mechanical power involvement should be there, what is mechanical power? Torque multiplied by speed. Okay, so in order to absorb mechanical power as a generator, or in order to deliver mechanical power as a motor, compulsorily torque is required. Okay, now in order to have continuous electromagnetic torque in all rotating machines, two conditions we have to meet at any cost. Okay, those conditions are: first condition, number of poles of stator and number of poles of rotor should be same, independent of any machine. It can be induction machine or DC machine or synchronous machine. This particular condition has to be met. Okay, and one question can be expected here. Okay, in induction machine, and one more thing is, this particular lecture is not meant for directly BTech studying students or who are about to start induction machine. For them this particular lesson will not help. Okay, for gate aspirants who have already done a bit of induction, at least overall view of induction, definitely this particular lecture will help you. Okay, kind of rotating magnetic field, for example, means how rotating magnetic field is going to be generated, I'm not going to discuss here. Somehow rotating magnetic field will come into picture. Okay, so because from there questions cannot come. Okay, anyway, number of poles of stator and number of poles of rotor should be same in any machine. Okay, in induction machine we are having two types of rotors. Our main focus is rotor only. Okay, two types of rotors will be there. One is squirrel cage rotor and another one is phase wound rotor or slip ring rotor. Phase wound rotor. Okay, now remember one point, that in squirrel cage rotor means squirrel cage rotor can be used for any number of stator poles. For example, one squirrel cage rotor can be used either for 2-pole stator or 4-pole stator or 6-pole stator, because squirrel cage rotor automatically will produce any number of stator poles. Okay, so this particular condition need not be checked for squirrel cage rotor. But if you think of phase wound rotor, okay, so phase wound rotor, intentionally you have to design your rotor in such a way that stator number of poles and rotor number of poles should be same. Okay, because it has to be separately wounded and all. Forget about the remaining discussion, because theory question only can come from here. Now, beyond that, one more point is there. In order to have continuous electromagnetic torque, first condition is this, and second condition is, means whatever may be the stator MMF and rotor MMF should be stationary with respect to each other, MMF only. Okay, it is not stator rotor. Okay, so it is stator MMF and rotor MMF should be stationary to each other. Okay, for example, in induction machine, if stator MMF is rotating with synchronous speed, rotor MMF also should rotate with synchronous speed, then only stator MMF and rotor MMF will be stationary to each other, such that continuous electromagnetic torque will be produced. Okay, so second condition is stator MMF and rotor MMF should be stationary with respect to each other. Okay, stationary with respect to each other. That's it. Okay, that's enough. That's more than enough. Now, let me think of induction motor. Okay, so in induction motor, let me think of black is stator. Okay, so here The moment you are going to supply to the stator, because normally we don't use rotor fed much in practice, but in the exam they can ask. Okay, so this is stator fed because we are feeding from the stator. Okay, so we are feeding means some fixed frequency supply to the stator, that is three-phase supply, okay, to the stator. So this can be called as stator fed. Okay, so in your exam, if they don't specifically mention, meaning that it should be stator fed only. Okay, if it is rotor fed, specifically they will mention. Okay, now let us think of stator fed. Now the moment you supply three-phase supply, forget about rotor for time being. Now the moment you supply three-phase supply to the stator, my MMF of the stator is going to rotate with synchronous speed. Okay, so let me think of an MMF pole structure, N pole here, S pole here, S pole here, and these NS poles of stator is going to rotate with synchronous speed. Let me think of that synchronous speed as NS. Okay, that NS equation is going to be 120 F by P. Everyone know about this. Okay, now if I think of frequency as 50 Hz, number of poles as 2, 120 into 50 divided by 2 is going to be 3000 RPM. Okay, I am taking this as a reference. Okay, now stator MMF with respect to stator is going to rotate with NS speed. Okay, for example, for time being, let us consider the NS speed as 3000 RPM. Now, if you think of the rotor, now my rotor, because of some interaction, electromagnetic interaction and all, we are not going to focus there much because no questions can come from there. Okay, now if you think of rotor, this rotor will rotate in the same direction. Okay, in the same direction of rotating magnetic field. Stator magnetic field, for example, if it is rotating in anti-clockwise direction, rotor also will rotate in the same direction but cannot be at NS synchronous speed. It is going to be with NR. That NR normally as a motor, NR rotor speed normally as a motor will be less than NS. Okay, now for example, let me define slip here. Okay, so slip is going to be stator MMF speed minus rotor speed divided by stator MMF speed. Okay, so for example, let me think of NR as 2700. Okay, and induction machine is called as asynchronous machine also. It is not asynchronous, it is asynchronous machine. Okay, asynchronous machine in the sense a machine which cannot rotate by itself at synchronous speed. Okay, now induction machine is asynchronous machine which cannot be rotated at synchronous speed by its own. Okay, so always my rotor speed should be less than stator MMF speed. That is called as slip. And slip is very important thing here, because in induction machine, slip is the only one independent variable. Okay, even if you recollect from our classes, it's fine, otherwise forget about it. Means slip is going to be very important factor or only important factor in induction machine. Okay, this is going to be the slip formula, NS minus NR by NS. Okay, now if I think of, see here, this is going to be stator is having fixed frequency supply, fixed frequency, because you are supplying with your power. Okay, with your input power you are supplying electrical power to the stator, so stator frequency cannot be changed. Okay, meaning that stator frequency, if you don't change, stator MMF speed 120 F by P frequency cannot be changed, so synchronous speed also cannot be changed. Okay, now if you think of rotor, just remember one thing, that in induction machine, okay, if you vary any torque requirement of the load, okay, because your induction motor, you are going to connect this particular motor shaft to the load. Okay, if load requirement is high, my rotor speed will be reduced. Okay, so if rotor speed is reduced, NS minus NR, for example, torque requirement of the rotor is reduced. Okay, meaning that my rotor speed is going to be reduced. Okay, if rotor speed is reduced, slip is going to be increased. Okay, so at my motor shaft, torque is going to be the only variable. Okay, because my load will be there. Now, for example, a motor will be there. This particular motor will be connected to load. Now, that load requirement, okay, what is the load requirement? Torque only will be there. So, the moment load requirement of the torque vary, automatically internally rotor speed is going to vary, meaning that slip is going to be vary. Okay, slip value will be decided by the load. That's it. Okay. Now, if I think of, if it is rotating with, stator MMF is rotating with 3000 RPM and rotor is rotating with 2700 RPM, what is the relative velocity between them, between stator MMF and rotor? I repeat, between stator MMF and rotor, relative velocity is going to be 300 RPM. Okay. Now, forget about the rotor for time being. When stator MMF is rotating with 3000 RPM, stator developed frequency is 50 Hz because I am supplying with 50 Hz. Okay. So, if I supply some voltage with 50 Hz, my back EMF will be there, no? Back induced voltage will be there, no? That back induced voltage also should be 50 Hz. Okay. Now, when stator MMF is rotating with 3000 RPM, you are getting a frequency of induced voltages, back induced voltages or back EMF of 50 Hz. Okay. Now, here if you see, when rotor is rotating with 2700, okay, now the moment rotor is rotating with 2700, my rotor 2700 in the sense my relative velocity is going to be 300 RPM. For 3000 RPM of the stator, if produced frequency are 50 Hz, for 300 RPM, how much will be the frequency of induced is going to be 5 Hz. Okay, so my frequency of the rotor is going to be 5 Hz. Okay, because if you are having 3000 RPM here, frequency of induced voltage are 50 Hz. If you have, means what do you say, rotating magnetic field which is rotating with respect to rotor, because already rotor is rotating with 2700. Okay, so my frequency is going to be 5 Hz. Now, let us think of slip. Okay, what is slip here? Slip is nothing but ns minus nr by ns. Okay, this is going to be the slip formula, keep it aside. Now, let me think of rotor frequencies. Okay, so rotor frequencies, let me think of this as the speed of the rotor. Okay, for example, if rotor is constant, in the sense stationary, okay, when the rotor is stationary, means with respect to rotor, my stator MMF will rotate with 3000 RPM only. Okay, so for example, if rotor is stationary, meaning that it will behave like a stator, whatever may be the frequency of induced voltage in the stator, same frequency of induced voltages will be there in the rotor also. When rotor speed is 0 RPM, my frequency is going to be F1. Okay, stator frequency only. Now, for example, if it is rotating with ns, when my rotor is rotating with synchronous speed, of course by its own it cannot rotate, but virtually if you calculate, when rotor is rotating with synchronous speed, my frequency of induced voltage are going to be 0. Okay, now if you think of rotor frequency is going to be SF. Okay, the moment frequencies are reduced, what about the rotor reactance? Rotor reactance also will be reduced in the same way. So let me think of rotor reactance. Rotor reactance is going to be S times X2. Okay, so what is this X2? X2 is going to be rotor standstill reactance. Okay, rotor standstill reactance, because frequency is reduced, meaning that reactance also should be reduced. Okay, now if you think of induced voltage, okay, rotor induced voltage also will vary in the similar terms. Okay, so if you think of rotor induced voltage ER, and this is rotor speed as NR, when rotor is not rotating, okay, stationary, when rotor is not rotating, 0 RPM, what will be the relative velocity between stator MMF and rotor? Stator MMF is rotating with respect to stator by ns, synchronous speed, or 3000 RPM. Rotor is not rotating, so relative velocity is going to be maximum, or slip is going to be 1. When nr equal to 0, slip is going to be 1. Okay, so rotor induced voltage is going to be maximum here. So this, let me think of this as E2. Okay, if rotor is getting rotated at synchronous speed, if rotor is rotating with synchronous speed, then rotor induced voltage is going to be reduced. So rotor induced voltage is going to be S times E2. S times E2, because see here, if you think of, if rotor is rotating with ns, okay, so ns minus ns, slip is going to be 0, so slip is going to be 0 here. When rotor is not at all rotating, under that condition, standstill conditions, so my nr is going to be 0, so ns by ns is going to be 1, so slip will vary from 0 to 1. Okay, in this SE2, what is meant by this E2 is going to be rotor standstill, 0 RPM, rotor standstill induced voltage. Okay, now rotor induced voltage is going to vary depending upon slip, and rotor frequencies are going to vary with respect to slip, and rotor frequencies also are going to vary with respect to slip. Okay, now this is the analysis. Now next thing is, actually here also multiple times questions came. Okay, now this is stator fed, because we are trying to feed from the stator fed, because we are trying to give supply, 3-phase supply to stator. Okay, rotor is going to be short circuited and all, like much analysis I don't want to enter. Okay, I don't want to entertain, but anyway, the moment it's stator fed, here frequencies are going to be constant, because we are supplying. Okay, so the moment frequencies are constant, what is Ns is going to be 120 F by P. Okay, the moment frequencies are constant, number of poles normally will be constant, because in speed control one time I will tell about pole change method. But anyway, as of now, number of poles for any machine is going to be constant. Okay, because number of poles for any machine should be decided at the time of design, not in the time of operation. Okay, so number of poles for any given machine is going to be constant, and if frequency is constant, if frequency of supply is constant, automatically my speed of the MMF is also going to be constant at Ns. Okay, now if you think of here rotor, okay, if you think of rotor here, my rotor is going to rotate with in this direction, in the same direction. Okay, in stator fed condition, whatever may be the direction of stator rotation, stator MMF rotation, in the same direction my rotor also has to rotate. Okay, so this is NR, okay. For example, my stator MMF is rotating with 3000 RPM, 2-pole machine, 50H machine. Okay, when my stator MMF is rotating with 3000 RPM, if my rotor is rotating with 2700 RPM, under that conditions, what is the rotor frequency is? My frequency of rotor is going to be slip times frequency. Okay, slip is going to be 10%, and my rotor frequency are going to be 5H. Okay, now the moment frequency of rotor is reduced, my speed of rotation of rotor MMF also is going to change. Okay, because see here, stator MMF and rotor MMF, if you consider, for stator MMF, stator number of poles and rotor number of poles should be same. So stator number of poles and rotor number of poles will be same. Okay, now stator frequencies are constant at 50 Hz. So stator MMF speed with respect to stator is going to be constant, that is 3000 RPM. Now if you think of rotor, okay, rotor is rotating with 2700 RPM, meaning that Ns minus Nr by Ns is going to give you 10%. Okay, 10% or 0.1 per unit. Now the moment slip is 0.1, slip times frequency, S times frequency is going to be 5H for the rotor. Okay, so the moment you are having 5H only in the rotor, under that condition means frequency is going to be SF. Okay, because SF, slip times frequency, so it is going to be SF, meaning that it is going to be SNS. Okay, so my rotor MMF with respect to rotor, okay, let me think of, my rotor is already rotating with 2700, and my rotor MMF with respect to rotor, okay, S in the sense it should be N, it should be S, fine. Okay, so SS, no, it should be N here, it should be S here, such that NS attraction, SN attraction, whatever it may be. See here, my rod, see here, always you have to focus here, because once we understand stator fed properly, means immediately rotor fed can be understood, and after that, once stator fed and rotor fed are over, remaining is going to be simple cakewalk with just equations, network theory, that's it. Okay. Now, see here, my stator MMF with respect to stator is rotating with 3000 RPM. My rotor physically is rotating with 2700 RPM. My rotor MMF with respect to rotor is going to rotate with 300 RPM. Okay, such that stator MMF and rotor MMF will have to become stationary, then only you are going to get continuous electromagnetic torque. Okay, let me repeat again. Focus. Okay, stator MMF with respect to stator is rotating with 3000 RPM. Okay, let me tell you, okay, in this way, for example, one train is there which is moving in this direction, maybe with 50 kmph. Okay, another train is moving adjacent to it. Okay, adjacent to it with, for example, 48 kmph. Okay, kind of stator MMF is rotating with 3000 RPM. Rotor is rotating with 2700 RPM. Okay, rotor is rotating with 2700 RPM. For example, in this train, inside this train, if you run inside the train with 2 kmph, okay, what will be the relative velocity between you and the other train is going to be 0. Okay, in the similar way, if you see here, okay, stator MMF with respect to stator is rotating with 3000 RPM and rotor is rotating with 2700 RPM, and with respect to rotor MMF is going to rotate in the same direction with 300 RPM, such that if you link the speed between stator MMF and rotor MMF, is going to be 0 RPM, or stator MMF and rotor MMF will become stationary to each other. Okay, now what are the conclusions we have taken here? Stator is provided with fixed frequency supply, that's why stator MMF will not change. And rotor, depending upon the load requirement, we know that rotor speed always should be less than synchronous speed. Okay, but how much less than synchronous speed, that will be decided by the load. Okay, now my rotor may rotate at 2900 RPM, or my rotor may rotate at 2500 RPM, or my rotor may rotate at 2700 RPM. Getting my point, right? So anyway, see here one conclusion. Okay, and one more thing is, if you are unable to understand, try to rewatch the video in future also. Okay, because we are about to enter into many things in one class. Okay, now see here, my stator MMF with respect to stator is rotating in anti-clockwise direction with 3000 RPM, and rotor is rotating in anti-clockwise direction only with 2700 RPM, and with respect to rotor, my rotor MMF is rotating in same direction with 300 RPM, such that my stator MMF and rotor MMF will become stationary to each other. That is the conclusion. Okay, now they will ask you questions like this. Okay, means you have to focus here, because from stator fed only I am going to get conclusions in the rotor fed also. Okay, now conclusion here is relative velocity. Okay, relative velocity between stator MMF and rotor MMF should be 0. Okay, so stator MMF and rotor MMF should be 0. Okay, now next thing is relative velocity between stator MMF and stator. Okay, of course you know this, I know, but let me extend this. Okay, now point here is, see here, relative velocity between stator MMF and stator. Okay, meaning that you are sitting on the stator. See here, stator MMF and stator. Okay, so the physically existing device or particular point is going to be stator. Okay, stator MMF just a minute, stator and stator MMF. Okay, stator and stator MMF will be decided by frequency. You are supplying constant frequency because it is stator fed, you are feeding through the stator. Okay, so the moment you are feeding through the stator, my stator MMF with respect to stator is going to be ns, synchronous speed, because frequency is constant f, it is going to be ns. If frequency is sf, it is going to be sns. That is for the rotor. Okay, now stator MMF and stator, you are sitting on the stator. Okay, is going to be ns. Okay, and after that, relative velocity between rotor MMF and rotor MMF and rotor. Okay, how much will be the relative velocity between rotor MMF and rotor, meaning that you have to focus on the frequency. Okay, how much will be the frequencies of induced voltage of rotor is going to be sf. So how much will be the relative velocity between rotor and rotor MMF is going to be sns. Forget about it. Now, these three questions normally they don't ask. One time, of course, they have asked velocity between stator MMF and rotor MMF in a sub question. Okay. Now, let us think of directly they will not ask these three. Now they will ask. Okay. See here, relative velocity. See, relative velocity between rotor MMF and stator. Okay, relative velocity between rotor MMF and stator. Okay, so the moment they ask you any question, okay, you have to observe for the physical parameter. Okay, physically existing point. Okay, rotor MMF is going to be rotating, but what is the physical existing point here? Stator. Are you sitting on the stator or rotor? You have to focus. Okay, so rotor MMF and stator, because conclusion is very simple. Okay, we know that relative velocity between stator MMF and rotor MMF should be same. Okay, now the moment you are sitting on stator and rotor MMF, don't try to visualize the things, it's not that much required. Okay, so stator and rotor MMF. Why to take rotor MMF? You can take stator MMF, no? Because stator MMF and rotor MMF will be stationary to each other. Okay, so just to confuse you, they will ask you this question saying like rotor MMF and stator. Okay, so the moment you decided to sit on stator, why to bother about rotor MMF or stator MMF? Anything is the same, because stator MMF and rotor MMF will be rotating at the same speed, stationary to each other. Okay, so the moment they asked you stator and rotor MMF, in place of rotor MMF, think of stator MMF only. Stator and stator MMF is going to be NS. Okay, so is going to be NS. Now they can ask one more question. Okay, because all these things we are going to extend to rotor fed. Okay, now they may ask you relative velocity between stator MMF and rotor. Stator MMF and rotor. Okay, now what is the physically existing point here? Basically, before answering any type of questions, first of all we have to understand where we are going to sit on the machine. Okay, so visualize here stator MMF and rotor. In between, relative velocity between stator MMF and rotor. Where are you going to sit here? On the rotor. Okay, so the moment you decided to sit on the rotor, why to bother about whether it is stator MMF or rotor MMF? Because in the space, okay, in the air gap, stator MMF and rotor MMF will be stationary to each other. So the moment they asked you, okay, so the moment they asked you means stator MMF and rotor MMF. Rotor is the physically existing point. Rather than stator MMF, you can replace rotor MMF. Okay, because stator MMF and rotor MMF will be stationary to each other. So rotor, physically existing thing. So rotor MMF and rotor. What is the rotor operating frequencies? Yes, F. Okay, slip times frequency. The moment you are having slip times frequency, it is going to be slip times NS. You understand my point? Right? Now, next thing here is only one more point you have to understand. Okay, so that is see here, when the stator MMF is rotating in anti-clockwise direction, rotor also will rotate in anti-clockwise direction only. Try to keep in mind. Okay, so direction, apart from this, direction matters. Okay, so when stator MMF is rotating in anti-clockwise direction, rotor also will rotate in anti-clockwise direction only. For example, if you want to change the direction of rotation of RMF of stator, okay, if you think of, see here, black. Okay, if you think of this as phase A, phase B, phase C. Okay, and if you supply currents of A, B, C, first A maximum will come, after that B maximum will come, and after that C maximum will come. Three phase currents. So first A maximum will come, after that B maximum will come, after that C maximum will come. Means my stator MMF will be rotating in anti-clockwise direction such that rotor also will rotate in anti-clockwise direction. Okay, now if I think of changing the direction of rotation of rotor, what I'm supposed to do? Rather than ABC phase sequence, if I give ACB phase sequence, then what's going to happen? First A maximum will come, A maximum will come, and after that C maximum, ACB phase sequence. First A maximum will come, after that C maximum will come, after that B maximum will come. So automatically direction of rotation of RMF of stator is going to be clockwise direction, such that rotor will be rotated in clockwise direction. Okay, so point to be remembered is very simple. In order to change the direction of rotation of RMF, just to change the phase sequence, everything fall in place. This is the thing. This is rotor fed. Okay, this is rotor fed. Why it is rotor fed? Because you are supplying your what do you say, input power, electrical power through rotor. Okay, electrical power at a constant frequency. So basically power we don't give, it will take automatically at a given voltages and at given frequencies we are going to supply. Okay, so the moment you supplied your power input here, okay, through power electrical power input, then frequencies of the source are going to be constant. Okay, so the moment of frequencies are constant, automatically my rotor frequency, because same supply, will go through slip rings. Okay, so here the moment here it is frequency is F, my frequencies of rotor is going to be F. Okay, now if you think of stator fed, okay, if you think of stator fed, in stator fed, stator is F, rotor is SF, rotor frequencies. And if you think of here, okay, in rotor fed, my rotor frequencies are constant at F, because supply frequencies are going to be constant. So what about my stator frequencies? It should be SF. It should be SF. Okay, I am not entering into too much into analysis, not required. Okay, that doesn't mean that I don't know. Okay, anyway, point here is very simple. Okay, my rotor frequencies are going to be constant, so stator frequencies will be decided by the load, that is nothing but slip. Okay, now for example, my rotor, okay, my rotor, the moment I supply some constant frequencies here, with respect to rotor, my rotor MMF has to rotate by ns, because frequency is constant and that particular ns is going to be 120 F by P. Okay, so my rotor MMF with respect to rotor is rotating with ns. With respect to rotor, my rotor MMF is rotating in anti-clockwise direction. Okay, now without going too much into analysis, simple. Okay, on floor, if I walk like this, I'll move forward. For example, if I do the same on treadmill, I will be constant, I will be stationary, but means what do you say, that particular belt will go backward. Okay, so point here is simple. Means if I am moving forward in this direction, okay, same movement is same, I'll go forward. But if I am stationary, but still if I'm able to walk, meaning that kind of treadmill, okay, so that particular belt will go back. Enough. Okay, so by the same strategy, by the same thing, not too much into analysis. Okay, so if it is rotating in this direction, my rotor is supposed to rotate in opposite direction. Just keep it in mind in that way. Okay, so my rotor MMF is rotating in this direction, meaning that my rotor has to rotate in opposite direction with less than synchronous speed. Okay, now what about the stator frequencies? My stator frequencies are going to be S into F. Okay, meaning that if I think of here, okay, so two poles are created. If I think of here, my stator poles, okay, because number of poles of stator and rotor should be same. Okay, the moment frequencies of stator now, okay, because we supplied power through the rotor, so stator frequencies are SF. So my stator poles has to rotate with the speed of SNS. Okay, in which direction? Ultimately we know that stator MMF and rotor MMF should be stationary with respect to each other. Okay, now my rotor MMF with respect to rotor, okay, so my rotor MMF with constant frequency, right, my rotor MMF with respect to rotor is rotating in anti-clockwise direction with 3000 rpm. Okay, now my rotor is rotating in clockwise direction with 2700 rpm. Okay, now if you sit in the space, okay, so if you sit in the space, air gap, Okay, basically I'm not discussing much into the analysis part. Okay, if I'm sitting in the space, my rotor MMF with respect to rotor is rotating in this direction with 3000 and rotor is rotating in this direction with 2700. So if you see, okay, my rotor MMF in space has to rotate in this direction with 300 rpm. Okay, let me check here. My rotor MMF with respect to rotor is rotating in this direction with 3000 rpm, and you are sitting here. Now my rotor MMF is rotating in this direction with 3000 rpm. My rotor is rotating in opposite direction with 2700 rpm. So my stator MMF, such that stator MMF and rotor MMF should be stationary with respect to each other, has to rotate in this direction with 300 rpm or SNS. Okay, such that, see here, my rotor MMF will rotate against to the direction of rotor, and my stator MMF also will rotate against to the direction of rotor, then only my stator MMF and rotor MMF will be stationary to each other, getting my point, right? Even if you don't understand much, don't try to analyze much. Okay, very simple. Means when rotor frequencies are F, stator frequencies are going to be SF. Okay, my rotor frequencies are F, my rotor MMF with respect to rotor is going to be NS. Okay, and stator frequencies are SF, so stator MMF is going to be SNS. The same thing whatever we have done in stator fed. Now let us see relative velocities. Now you will understand, or at least you will try to remember the things. Okay, now see here, relative velocity between stator MMF and rotor MMF. Okay, both MMF should be stationary or not? Yes. So it should be 0 rpm. Okay, now let us think of relative velocity between stator MMF and stator. Okay, stator MMF and stator only. So in stator, see here in rotor fed induction motor, I'm thinking the moment in rotor frequencies are F, stator frequencies are going to be S times F. So my stator MMF and stator is going to be SNS, because ultimately my speed of rotation of MMF is going to be 120 F by P. P cannot be changed. 120 F directly proportional to F. Okay, if frequency is SF, my speed of rotation is going to be SNS. That's it. Okay, now let us think of relative velocity between, okay, rotor MMF and rotor MMF and rotor only. Okay, rotor MMF and rotor only. How much it should be? Rotor means what are the operating frequencies of rotor? Operating frequencies of rotor is going to be F here. Okay, meaning that with respect to rotor, my rotor MMF has to rotate with NS, synchronous speed is going to be NS. Okay, now let us play with it. And here we have to remember one thing, that with respect to direction of RMF, rotor will rotate against to the direction of RMF. Okay, or stator MMF or rotor MMF will rotate against to the direction of rotor. Okay, anything is fine. Now let us think of relative velocity between rotor MMF and stator. Rotor MMF, you need not bother much, just where you are going to sit matters. Okay, in the complete machine, means in the physically where you are going to sit on the machine, you have to understand. See here, stator and rotor MMF. Okay, on which part of the machine you are going to sit? Stator. Okay, you are going to sit on the part of machine which is stator. The moment you are sitting on the stator, why to bother about rotor MMF? Because stator MMF and rotor MMF will be stationary to each other. Okay, so rather than taking rotor MMF, let us think of stator MMF. Stator MMF. Now stator and stator MMF. Stator and stator MMF. Stator and stator MMF. Meaning that what is the operating frequency of stator in rotor fed induction motor? SF. So it is going to be SNS. Getting my point? Right? Now let us think of relative velocity between stator MMF and rotor. Stator MMF and rotor. How much it will be? Okay, see here, stator MMF and rotor. Which part of the machine you are going to set? Stator MMF and rotor. Okay, so either you can sit in the stator or you can sit in the rotor or you can sit in the space. Okay, if you are sitting in the air gap, meaning that you are sitting on the stator only. Okay, now in between stator MMF and rotor, you are going to sit on the rotor. Okay, so the moment you are sitting on the rotor, why to bother about stator MMF? Think of rotor MMF only, because rotor MMF and stator MMF are stationary to each other. So stator MMF is not required. Let us think of rotor MMF. Okay, so rotor and rotor MMF, meaning that what is the operating frequency of rotor? We are supplying to rotor now. So operating frequency of rotor is going to be F only, supply frequency only. So it is going to be NS. Okay, so in this way we have to understand. Okay, and as per that, definitely in rotor fed or stator fed, multiple times they ask the questions. Okay, as per that we have to conclude this way. Let us see rotor circuit analysis, the heart of induction. Okay, if you see previous like old gate questions or old IES questions, or if you think of upcoming gate 2021 questions from induction machine, at least 70% probability will be there that questions or problems can come from this area only. Okay, kind of speed control, yes, this area only, and kind of braking, yes, this area only, and normal questions also from this area only. Okay, because rotor circuit analysis is the heart of induction. Okay, anyway, if you think of rotor circuit equivalent, okay, rotor circuit equivalent is going to be like this. Okay, here rotor induced voltage ER will be there, and here rotor reactance XR, and here rotor resistance R2. Okay, and in our previous session we mentioned that rotor frequency is going to be S times slip times stator frequency is nothing but rotor frequency. So the moment frequency is reduced by slip times, automatically this is going to be S into X2. X2 is the like standstill condition rotor reactance. And if you think of here, rotor induced voltage will be decided by the relative velocity between stator MMF and rotor. Okay, so this is going to be slip times rotor steady state induced voltage. Okay, and here current is going to be I2. Okay, now whatever may be the current is coming here, equivalently we can transform this circuit because of some reasons. Those reasons are not required as of now. Okay, this is going to be the rotor circuit model. Okay, actually many times many students feel that induction machine, so many topics are there. No, if you learn this particular topic, speed control, braking and all, just like that you will be able to solve. Okay, now equivalently we can transform this into, this is divided by S. If I do that, impedance is going to be divided by S and induced voltage is going to be divided by S, such that same magnitude of current has to be there. Okay, so same magnitude of current should be there. Rotor current. Okay, everything is referred to stator side. Okay, means from transformer's point of view, if you see, I am supposed to write R2 dash, XR dash or SX2 dash, something like that. Okay, anyway, dash and all, reflections and all, like from rotor side to stator side how to reflect, or from secondary side to primary side how to reflect. In transformer only we know. Okay, so automatically they are going to give reflected values only without using dash dash dash, something like that. I am considering, that's it. Okay, and here divided by S will give you X2, and here divided by S will give you R2 by S, here divided by S will give you E2. Okay, in which case actually from this case to this case frequency independence will come and all. That's a kind of analysis which are not required as of now. Okay, same current is going to be there in both the cases. Okay, let me write equation for I2 is going to be E2 divided by R2 by S square plus X2 square, and the root is going to be rotor current. Okay, or rotor current reflected to stator side, whatever it may be. Okay, and means once slip is there, in our previous session also I clearly mentioned, okay, in induction machine slip is the only independent variable which will be decided by the loading conditions. Okay, depending upon the load connected, slip is going to vary. So the moment slip is going to vary, because slip is the only independent variable and all already I said. Okay, so slip is going to be independent variable. Depending upon the load, it's going to change. Now this is going to be the rotor circuit. Okay, now if you think of rotor power input to the rotor circuit, which is called as air gap power, PG. Okay, so this is called as air gap power. From air gap, how much power is being taken by the rotor? Okay, we know that reactance will not absorb any active power. Power in the sense, what I mean to say is active power. And one more thing is, active power only will be transformed into torque, speed. Okay, because one thing I may have to share here. If you think of synchronous machine, okay, synchronous machine may absorb reactive power, may deliver reactive power. Okay, for example, if you think of synchronous motor, okay, synchronous motor may absorb reactive power, may deliver reactive power. For example, many students this kind of confusion will be there. Okay, so they feel that, for example, synchronous motor is there. Okay, synchronous motor is absorbing active power. Why it absorb active power? In order to deliver active power in the name of mechanical. Okay, synchronous motor will take active electrical power, will deliver active mechanical power at the shaft. But if you think of reactive power is not a power. Okay, so synchronous motor may absorb reactive power, it will not be delivered into shaft because it is reactive power. Reactive power is not a power. Reactive power is not a power. Okay, means reactive power compensation and all, it's a matter of power systems, forget about it. Okay, so always when we say power, shaft power, okay, so the moment it's a shaft power is nothing but active power only. Reactive power will not come to the shaft. Okay, anyway, if I think of active power absorbed by the rotor circuit, or which is called as air gap power. Okay, that air gap power actually from stator side is delivering that much active power to the air gap, and from the air gap my rotor is going to take that power. Okay, now at starting you may feel all these things we know and all. Okay, but logic here is extension. Okay, so connecting the dots, most of the guys may not know, that is called as revision, right? Now PG is going to be, how much is PG? I2 square R2 by S, because this is the resistive term. Okay, resistive term only will absorb active power. Okay, if I think of number of phases, if I think of 3-phase induction motor, multiplied by 3, because everything is going to be per phase value. Okay, let me think of M. M is nothing but number of phases. For 3 phase you are supposed to keep 3. Okay, now one thing here is, if I connect with other machines, okay, induction motor always efficiency will be less than 1, including under ideal conditions also. For example, if you think of DC generator motor, okay, ideal conditions efficiency will be how much? 100%. If you think of transformer, ideal conditions efficiency is going to be 100%. Okay, if you think of synchronous machine, ideal conditions efficiency is going to be 100%, but in induction machine, ideal conditions, for example, R2 equal to 0, rotor resistance is 0. When rotor resistance is 0, power absorbed by this is going to be 0. So when air gap power is 0, okay, power to be transmitted to rotor circuit, which is nothing but air gap power, when air gap power is 0, how much will be the output power? Output power will be 0. Okay, so my R2 rotor resistance should be non-zero, then only induction motor will work. The moment R2 should be non-zero, meaning that rotor copper losses in the worst case also it should be there. Okay, so you may neglect core loss, you may neglect copper loss of stator, you may neglect mechanical losses because rotor has to rotate and all, but at any cost you should not neglect rotor copper losses, because rotor side rotor resistance should be there. Rotor resistance should be there. Anyway, keep this point in mind, that's enough. Now this is going to be M into I2 is going to be how much? This is E2 square by R2 by S square plus X2 square into R2 by S. Okay, now let me transform the same model into again equivalent model. Let me use maybe black again. Okay, if I transform this into again equivalent circuit, okay, I can divide this R2 by S into 2 terms because rotor resistance should be there. Okay, for example, if I divide like this, rotor reactance, rotor resistance, and some other external resistance. External resistance is some extra part. Okay, same E2, same I2, same X2, and here R2, R2. Why? I want to divide rotor copper losses separately and rotor resistance is R2, and this particular value is going to be R2 by S into 1 minus S. Okay, for example, power input to the rotor circuit is PG, air gap power. Out of that power, compulsorily rotor copper losses has to be deducted. Okay, because R2 plus R2 by S into 1 minus S is going to be R2 by S only. Okay, so this R2 by S only we split it into two terms, such that rotor copper losses may have to be deducted from the air gap power. So air gap power minus rotor copper losses means what is this? What is this particular resistance? This particular resistance of R2 into 1 minus S by S will not be there in the physical world. But why this came? This is equivalent to the power transformed to the mechanical side. Okay, details forget about it. Now, point here is, if I think of rotor copper loss, rotor copper loss at any cost, it will be there in all practical conditions of the induction motor. Okay, rotor copper loss is going to be how much? I2 square R2. Okay, now if I think of air gap power, that is nothing but power input to the rotor circuit minus rotor copper loss, minus rotor copper losses is going to be how much? Is going to be power delivered to mechanical side. Okay, of course, friction losses when to deduct, or kind of core losses when to deduct, copper loss when to deduct. From those point of view, we will discuss in efficiency calculations or power flow calculations later. Okay, but as of now, my concentration is rotor circuit. Okay, now this is going to be power developed. Okay, so air gap power minus this is going to be power developed equivalently, which will be converted into mechanical side. Okay, now out of this power, whatever is there, maybe PD, out of PD, if you deduct mechanical losses, shaft power will come. Okay, about that we will see later. Okay, as of now, this is going to be the thing. Now, what is power from a mechanical point of view? Torque multiplied by speed is going to be power. Okay, or I can say that developed torque, mechanical equivalent developed torque inside the rotor circuit is going to be power developed divided by rotation of the rotor circuit. What is rotation of the rotor circuit? Is going to be omega R. Omega R, enough. Okay, now let me convert this into, what is PD here? PD is going to be I2 square. See here, I2 square into R2 into 1 minus S by S. Now if I think of PD, which is going to be I2 square into R2 by S into 1 minus S. Okay, now if you see here, see, means if you think of PG, I2 square R2 by S, I2 square R2 by S is going to be air gap power, and developed power is going to be I2 square R2 by S into 1 minus S, into 1 minus S. So this can be written as PG gross power, which is coming from the air gap power, into 1 minus S. Okay, logic you will come to know. As of now, you may feel that okay, it's easy, only you will be able to do it. No, it's not like that. Connections will be there. Okay, if you connect the dots properly, then it will be very easy to solve problems of speed controller, whatever it may be. Okay, so PG into 1 minus S. Now let us think of omega R. Now if I think of slip, what is slip? Is going to be omega S minus omega R by omega R in radians per second, and in RPM, NS minus NR by NS will come. Okay, now with this, omega R is going to be how much dear? S into omega R minus omega S will be there. If I send it to the other side, it's going to be omega S into 1 minus S, omega R. Now come back to torque. Okay, developed torque. What is developed torque? PD divided by omega R. Now what is PD? PG into 1 minus S divided by, what is omega R? Omega S into 1 minus S. Cancel this. Okay, then this is going to be PG by omega S. Okay, now for further calculations, for example, if you want to calculate maximum torque, okay, means gradually you will get maximum torque will be decided by the machine, starting torque will be decided by the machine, but running torque will be decided by the load. Those things gradually you will get. Okay, now if you think of, means if you want to calculate maximum torque developed, okay, in order to calculate maximum torque developed, we should be able to differentiate this, or we should be able to differentiate this. Okay, now if you think of omega R, is it variable or constant? is variable, because in induction machine slip is going to be the independent variable. The moment slip varies, automatically omega r is going to vary, and at the same time PD is also variable. Okay, now if you think of same PD by omega r is nothing but PG by omega s. So if you think of this equation, PG by omega s equation, in this particular equation omega s is constant or not? Yes, 120 F by P. Okay, so that is going to be stator frequency. If you think of stator fed induction motor, whatever may be the frequency you are supplying to stator will decide ns or omega s. Omega s, right? So here in this equation omega s is going to be constant. Okay, now if you want to calculate pull out torque or maximum torque, okay, pull out torque or maximum torque or stalling torque, everything is going to be same. Now if I think of calculating the maximum torque, means in order to calculate maximum torque we should be able to differentiate only PG or TD, or my developed torque is going to be maximum when PG is going to be maximum. It is sufficient condition because omega s is constant. But if you think of this particular equation, TD equal to PD by omega r. Okay, so in this equation PD by omega r should be maximum, which is difficult actually to calculate, lengthy. So means for developed torque we are fixing this equation, TD is going to be PG by omega s. Okay, now let me show you one thing such that you will never ever forget. Okay, see here, if I want to calculate torque developed, okay, so air gap power or total power supplied to the rotor circuit is PG. Okay, total power supplied to the rotor circuit is PG, and power developed, mechanical power equivalent developed is PD. Okay, now you can think of PD by omega r. Omega r is nothing but the real speed of the rotor circuit. PD by omega r can be taken, or PG by omega s can be taken. So for all further analysis, okay, we are going to consider PG by omega s only, PG by omega s only, because omega s is constant such that denominator is going to be removed. Okay, because it's going to be constant. Okay, now developed torque is going to be PG by omega s. What is the air gap power? What is the air gap power? See here, what is air gap power? Is nothing but total power supplied to the rotor circuit. How much is the total power supplied to the rotor circuit? Whatever may be the power absorbed by this. What is the power absorbed by this? I2 square R2 by S. Okay, so if I try, basically you are supposed to keep this small circuit in mind such that 70% of the problems asked in induction machine can be easily solved. Okay, so just keep this particular circuit in mind. It's a small circuit only, but okay. Now the thing here is, just a minute, yeah, so this is going to be m number of phases divided by omega s. Okay, now what is per phase? Per phase PG air gap power is going to be I2 square R2 by S. Problem solved. Okay, now if you want to calculate maximum power, okay, so let me draw it again, because as many times as possible try to draw this diagram. Most of the problems automatically can be solved. Okay, now this is x2, this is R2 by S, and this is rotor standstill induced voltage E2, and this is I2. Okay, now what is PG? What is PG? PG is going to be air gap power, is going to be power absorbed by this particular resistance. Okay, when this PG is going to be maximum, at that point automatically developed torque also is going to be maximum, because omega s is constant. Okay, now in order to calculate pull out torque or maximum torque or stalling torque, okay, so let me think of TEM, electromagnetic maximum torque. Okay, TEM or TDM, TE or TD is same. Okay, some textbooks they may write TE, electromagnetic torque, or maybe some textbooks they may write developed torque. Both are same. Okay, now if you think of pull out torque or maximum torque, at maximum torque PG should be maximum. PG is nothing but the power absorbed by this should be maximum. Maximum power transfer theorem of network theory can be applied. Okay, now at TEM what is the condition? In order to have maximum power here, so this particular impedance value should be equal to this particular impedance value, or this particular resistance value should be equal to reactance value, so such that R2 by SMT should be equal to X2. Okay, because slip at which maximum torque occurs, because slip is the variable. If you see, rotor reactance is constant value, rotor resistance is constant value, but slip is going to be variable value. Okay, now let us think of, see here, at a TEM, magnitude of this R2 by SMT is going to be X2, or I can rewrite this as a SMT equal to R2 by X2. Fix this. Okay, now let us write the equation for TD is going to be m by omega s into I2 square R2 by s. I2 square R2 by s. What is I2? I2 is nothing but E2 divided by, okay, simple thing. Now let us write this as m by omega s into E2 square divided by R2 by s square plus X2 square into R2 by s. Okay, this is going to be torque equation. Just we are going to remember this. Frankly speaking, we are not going to remember this also. We are going to remember this small thing. Okay, this is normal torque. Now let us calculate pull-out torque. Okay, if I try to calculate pull-out torque or maximum torque, okay, TEM is going to be how much? M by omega s into E2 square. Okay, so maximum torque in the sense R2 by SMT should be used. Okay, maximum torque in the sense R2 by SMT, in place of slip SMT should be used. Okay, R2 by SMT equal to X2. Okay, R2 by SMT equal to X2. So E2 square divided by maximum torque R2 by SMT, slip at maximum torque occurs, is going to be X2, X2 square, 2X2 square, and R2 by SMT is going to be X2. Okay, such that this is going to be the case. M by omega s into E2 square by 2x2 is going to be pull out torque or maximum torque, and this is going to occur at R2 by SMT equal to x2. Okay, or I can rewrite this as a slip at which maximum torque occurs is going to be R2 by x2. Okay, now if you see magnitude of, keep this particular point in mind. Okay, so magnitude of maximum torque is independent of rotor resistance. Rotor resistance is not there, and slip at which maximum torque occurs will be decided by rotor resistance. Okay, rotor leakage, actually some of our guys told me that even some online test questions some guys formed by varying x2. Okay, it is not practical. At any cost, x2 should not be varied. Okay, just for our operation convenience, maybe rotor resistance can be changed, but rotor reactance can never ever be changed. Okay, anyway, forget about it. Now point here is, one time they asked magnitude of maximum torque is inversely proportional to standstill rotor reactance. Okay, something like that. Anyway, point to be noted here is pull out torque, magnitude of maximum torque is independent of rotor resistance, but slip at which maximum torque occurs will be decided by rotor resistance, will not be decided by rotor reactance. Okay, because the MSQ questions are there, no? We should be ready for MSQ questions also. So x2 we are not supposed to change at any cost because of some reasons, forget about it. Okay, now let us think of, this is the maximum torque. Okay, now let me think of normal running torque. Okay, now TD or TE is going to be m by omega s into E2 square divided by R2 by s square plus x2 square into R2 by s. Okay, just don't watch the video just like that. Take pen and paper. You please write, because this particular equation, if you write as many times as possible, if you write, automatically remaining things will come into hand. Okay, now basically right now we will be able to solve all speed control problems or some kind of problems. Okay, anyway, I'll keep it aside. Okay, such that in future I'm going to take from here only and I'm going to analyze. Okay, now see here, normally in machines, okay, x by r ratios, if you think of x by r ratios of machines will be at least more than 2. Okay, normally in transformer it will be more than 2 x by r ratio, and in induction machine it will be more than 5. Okay, or in synchronous machine it can be more than 10, but anyway x by r ratio of any machine will be at least more than 2, meaning that x value will be more than resistance. Just keep this point in mind. Okay, now anyway pull out torque value we got and slip at which maximum torque occurs we got, and a normal run, because now you are going to get a clarity, okay, about the starting torque, running torque, pull out torque and all. Okay, just stay tuned, because in small things only students are much confused. Okay, anyway, point here is this particular torque, let me divide it into two cases. Okay, means high slip region and a low slip region. Okay, what is slip actually? Slip is nothing but ns minus nr by ns. Okay, the moment slip is less, what does it mean? Ns minus nr should be less, because anyway ns is constant in the denominator. Okay, ns minus nr should be less, meaning that nr should be nearer to synchronous speed, in the sense running conditions. Okay, so once induction motor, okay, there are two conditions will be there. One is just if you start the induction motor. Okay, when you start the induction motor, my rotor speed is going to be almost 0. Okay, or at starting it will be 0. In starting conditions it will be much less. Okay, and once it go to running condition, at running condition ns minus nr value is going to be much less. Okay, so if I think of low slip region, it is going to be running conditions. If you think of high slip region, it is going to be starting conditions. Okay, in low slip region, if you think of, think of only denominator, don't think of numerator. Okay, so if you think of R2 by S, low slip region, slip is less. For example, slip is 10%. In the sense slip is going to be 0.1. R2 by 0.1 is going to be 10 times R2. Okay, so in this case R2 value is going to be more compared to X2 value. So let us neglect X2. Okay, is it practical to neglect and all? It's a different story which will take much time and all. Anyway, for time being, because it's meant for revision. Okay, so in low slip region, the moment slip is less, R2 by S value is going to be more. So R2 by S is going to be more compared to X2. Neglect X2. If you neglect X2, TD is going to be m by omega s into E2 square. R2 by S is going to be more, so we have to keep it divided by R2 by S square into, in the numerator, R2 by S. So R2 by S and R2 by S is going to be cancelled, such that this is going to be m by omega s into E2 square by R2 into S. Okay, stay tuned, because multiple times you do this mistake, or most of the guys. Now high slip region, if you think of high slip region, my R2 by S, this is the torque equation, right? So in this torque equation, slip is high, meaning that it would be really nearer to unity. Okay, NR, starting condition, which will be much less. If you think of at starting only, how much will be the rotor speed? Is going to be 0. So when rotor speed is 0, ns minus 0 by ns is going to be 1. High slip region. Okay, so when slip is nearer to 1, then slip is nearer to 1. Okay, X value is going to be more than R value. The slip is nearer to 1. Under that conditions, X2 values are going to be more compared to R2 by S value. So neglect R2 by S. Then my TD is going to be m by omega s into E2 square by X2 square into R2 by S. Okay, now here one thing we have to decide, that is, they can ask only starting torque, they can ask peak torque, okay, but they cannot ask during starting condition, because during starting conditions it's a transient period. For example, the moment you started on induction motor, okay, at that instant, just about to start, at that instant, how much is the torque developed, anybody can ask. But after that, means it will be accelerated. That rotor speed will be accelerated towards synchronous speed. During that time of acceleration or in the transient period, nobody can ask any question. Okay, so let me directly write starting torque is going to be how much? Starting, how much is going to be the slip? Is going to be 1. So this is going to be E2 square by X2 square into R2. That's it. Okay, we are all set to solve directly the problems of speed control also. Okay, anyway, see here, this is going to be the thing. Okay, in between, how much is the maximum torque? Maximum torque is going to be m by omega s into E2 square by 2x2, and slip at which maximum torque occurs? is going to be R2 by X2. Now we should be able to draw the characteristics of this. Okay, do they ask characteristics? No, they don't ask, but we should understand this at least. Okay, now if you see, okay, if you see kind of drawing the characteristics, this is going to be the torque developed by the motor. Okay, torque developed by the motor, and this is going to be the rotor speed, zero speed, ns speed, rotor speed. Yes, fine. Okay, or from slip point of view, we can say that this is going to be the slip, this is zero slip, this is unity slip. Okay, now means low slip region in the sense nearer to 0, and high slip region meaning that nearer to 1. In between, pull out torque will be there, or maximum torque that can be developed by the motor will be there. Maximum torque that can be developed by the motor is TEM. Okay, so TEM is going to be the pull out torque. Now, slip at which maximum torque occurs will be decided by R2 by X2. So, slip at which maximum torque occurs, for example, this is slip at which maximum torque occurs, this is SMT. Now, in low slip region, this is low slip region, right? In low slip region, if you don't vary anything, okay, you are not going to vary rotor resistance, you are not going to vary kind of number of phases, you are not going to vary frequency, everything is fixed, okay, without going to speed control and all, everything is going to be constant. So, TD directly proportional to slip. Slip is independent variable. Okay, so directly proportional to slip is going from 0 to 1, meaning that it should be a straight line. It should be a straight line. It should be a straight line. Straight line. Now, if you think of starting conditions, okay, if you think of starting conditions, means when everything is constant, m by omega s is constant, E2 by X2 is E2 and X2 are constant, R2 are constant. So, in these conditions, my high slip region torque inversely proportional to slip. Inversely proportional to slip, and starting torque will be there. Starting torque, we cannot say that starting torque will be 0 and all, starting torque will be there. So, starting torque is going to be inversely proportional. Okay, now if I try to draw the characteristic, okay, it's going to be straight line, and after that it is going to be like this. So, my torque speed characteristics or torque slip characteristics of induction motor will be like this, provided y-axis is torque developed and x-axis is rotor speed, or in opposite direction it is going to be the slip. Okay, now pull out torque is the maximum torque. Now, this is going to be the starting torque, TST. This is going to be the maximum torque. Okay, now you will get clarity now. Just wait. Okay, so my characteristics are like this. Characteristics are like this. This is going to be slip equal to 0. This is going to be slip equal to 1. This is slip. This is rotor speed. That's fine. Okay. Here it is going to be straight line, and after that it is inversely proportional. And this is pull out torque, TEM. This is going to be the thing. Okay. Now let us think of kind of speed control, kind of parameter variations. Okay, now see here, this is the starting torque equation, because you should get this clarity. Without this clarity, if you attempt the question, means you can ruin the paper. Okay, so see here, for example, rotor resistance is doubled. Okay, I repeat, for example, rotor resistance is doubled. Focus here, please. If rotor resistance is doubled 2 times, then how much will be the starting torque? 2 times. Okay, so when rotor resistance is doubled, for example, under that condition starting torque will be doubled as per this equation. Okay, now if you think of pull out torque, if rotor resistance is doubled, okay, so m by omega s into E2 square by 2x2, so rotor resistance magnitude or value is not there here in this particular equation, so pull out torque will not change. Okay, now let us think of running torque. Because this is running conditions. No, in running conditions, for example, rotor resistance is doubled. Can I say running torque will be half? No. Okay, see here, that's what we have to focus. Okay, now starting torque will be doubled, yes, by this equation, because rotor resistance is there in the numerator. Starting torque is going to be doubled if you double rotor resistance. Okay, now pull out torque. Pull out torque is independent of rotor resistance, so pull out torque will not change if you double the rotor resistance. But if you double the rotor resistance here, okay, in the denominator, if you double the rotor resistance, my torque developed is going to be reduced by half is wrong. Because keep this particular point in mind, this is very crucial. Okay, starting torque will be decided by the machine. Okay, and peak torque or maximum torque or pull out torque will be decided by the machine, but running torque will be decided by the load. Who are you to decide? Okay, for example, question has to be understood this way. Okay, for example, rotor resistance is doubled. Rotor resistance is doubled in running conditions. Rotor resistance is doubled. When rotor resistance is doubled, in order to maintain the same load torque, I repeat, in order to maintain the same load torque, means how much will be the slip, they can ask. Okay, because this particular torque requirement of the load, okay, when developed torque by the motor equal to torque requirement of the load. Okay, if torque requirement of the load is 150 Newton meters, 150 Newton meters for example, in order to meet 150 Newton meters, your machine has to adjust itself. Okay, now for example, for given 150 Newton meters, torque requirement is constant by the load. When torque requirement is constant by the load, okay, if rotor resistance is doubled, slip also will be doubled in order to meet the same load torque requirement should be the analysis. Okay, for example, on any motor you are increasing the torque requirement. Okay, for example, 50 Newton meters torque requirement of the motor, 50 Newton meters, you increase to 100, you increase to 150, you increase to 200, you increase to 300, 400. For example, maximum torque that may be delivered by that particular motor is 500 Newton meters, maximum pull out torque. Okay, so if maximum that can be delivered by the motor is 500 Newton meters. Okay, for 50 Newton meters it work, for 100 Newton meters it work, for 350 Newton meters it work, for 450 Newton meters it work. Okay, for 500 Newton meters also it work, because pull out torque. Okay, beyond 500, if load requirement is 600 Newton meters, it cannot deliver, my rotor will be stopped. Okay, so means till your running torque requirement of the load is less than pull out torque, motor will rotate. If your torque requirement of the load is more than pull out torque, my rotor is going to be stopped. That's it. Getting my point, right? So running torque requirement will be decided by the load. Just keep this point in mind. Starting torque will vary, pull out torque may vary. For example, means I'm directly connecting this to speed control without actually using the name speed control. Okay, for example, E2 doubles. Okay, doubles may not be good idea. For example, E2 is reduced by 10%. Okay, E2 is reduced by 10%. When E2 is reduced by 10%, in the sense 90% of rated voltage when you supply, right? 90% of rated voltage when you supply, now starting torque will be reduced by 20% or 19%. Okay, because 0.9 square will give you 0.81. So 81% of previous torque will be there, or 19% starting torque reduction will be there. Okay, so starting torque will be decided by the machine. Okay, for example, at starting, okay, pull out torque is 500 Newton meters, and at starting, for example, it is 50 Newton meters. Okay, when you about to start the motor, it is able to deliver 50 Newton meters. At starting only, if your torque requirement is more than 50 Newton meters, it will not start. Okay, now means my starting torque developed by the motor is 50 Newton meters, and your torque requirement of the load is 10 Newton meters at starting, for example. At starting, then 50 Newton meters my motor developed, and 10 Newton meters like my load requirement at starting. So 50 minus 10, 40 Newton meters, extra 40 Newton meters will be delivered to accelerate the rotor. Okay, so always keep this point in mind. Starting torque will be decided by the motor. Pull out torque will be decided by the motor, but main running torque will not be decided by you. That will be decided by the load. Okay, anyway, coming to the point here, for example, E2 is reduced by 10%, then starting torque will be reduced by 19%, 19%, or starting torque maintained will be 81% of previous torque. Now, if you think of pull out torque, maximum torque, now if you think of reducing E2 by 10%, okay, meaning that you reduce it to 90% of the rated voltage, under that conditions pull out torque is going to change. Okay, but you should never ever say that running torque is going to change. Okay, because for example E2 is reduced. Okay, in running condition this is the case, right? So E2 is reduced by 10%. E2 is reduced by 10%, meaning that this particular E2 square will be reduced by 19%. But torque requirement of the load is constant. For example torque requirement of the load is constant. Under that condition, my slip has to change itself. Such that torque requirement of the load has to be furnished by the motor. Okay, so in this condition only one point you have to keep it in mind, that is running torque requirement will be decided by the load. Starting torque and pull out torque will be decided by your motor. Okay, so E2 is reduced, so starting torque is reduced, fine. Running torque reducer should not be said, but pull out torque is reduced is fine. Getting my point, right? So as of now, even in speed control also, braking also, we are going to do the same thing. Okay, that same thing is, see here, where is this particular just a minute, this particular diagram we are going to remember. Okay, E2 X2 R2 by S, and if you think of PG, okay, air gap power, and M by omega S of PG is going to be the developed torque. Okay, now PG is nothing but, see here, M by omega S into I2 square R2 by S. Okay, in place of I2 you are going to place E2 by square under root. Okay, and after that you are going to divide these two, or this particular equation, into two splits. Okay, running condition, in running condition slip is going to be less, and starting conditions, in starting conditions slip is going to be more. So high slip region, low slip region, depending upon the question asked. Okay, for example, if they ask some variation happened, rotor resistance is double, what will happen to starting torque? Yes, you have to answer it. Okay, so means as per that, running condition, starting condition we have to split, and depending upon the question, running condition in the sense, okay, running condition related equation we are supposed to consider. That's it, it's damn simple. Okay, so running condition, if they ask you this particular equation, we are going to consider. Now don't remember this equation, directly remember that particular small diagram only. From there automatically we will be able to draw in the exam. Okay, and remaining extension I will see in speed control. Now let us see here stable unstable points we should know. Okay, now multiple times they have given questions. Now if I think of, this is torques. Okay, now for example this is torque developed by the motor. Okay, and if I think of this as torque requirement of the load, I need not say that always torque requirement of the load is constant, because for example solid to solid friction torque requirement will be constant, kind of metal cutting tools and all, multiple times I said. And if you think of torque required for solid to liquid, torque requirement will be directly proportional to speed. And if you think of solid to air, kind of ceiling fan or fan load, under that condition torque requirement of the load will be directly proportional to speed square. Okay, so depending upon the load requirement, it will have its own characteristics. Okay, now what are the points which will be stable or not, we should be able to understand. Okay, so how to calculate that? Maybe if I think of this particular point and this particular point, right? Because at this particular point and at this particular point only, developed torque equal to load torque. Developed torque by the motor equal to torque requirement of the load, then only stable conditions will be there. Okay, so this particular point and this particular point, which is stable point? Don't analyze, because before going any further, increment in speed direction we should know. Okay, for example, if I give direction of speed is in this direction, then analysis will be different, or output or conclusion will be different. If I change direction of speed in this direction, everything is going to be changed. Okay, now remember one thing, which color? Maybe red only. Okay, so always keep this point in mind. In increasing direction of the speed, this is the stable operating point. No, that is the interconnection point. No, after that drive one line in the direction of increasing speed. Then if you think of here and here, okay, so black is torque developed by the motor and blue is torque requirement of the load. Okay, so after this junction point, what is happening? Torque requirement of the load is increasing, torque developed by the motor is going to be reduced or less. Okay, so then what will happen? Torque requirement of the load. Okay, so load is requiring more torque, but my motor is unable to give that much torque, so that is going to be decelerating torque. So my operating point will not travel towards this, so it is going to be stable. Okay, now if you think of here, let me draw one line immediately after this junction point. Okay, in the increase in direction of speed, let me write like this. Okay, in increasing direction of speed, then what will happen immediately after this particular point in direction of increase in speed, after the junction point, go through it, and this is going to be the torque and this blue line is going to be the torque. Okay, so this red line is more. What is this? This black line is more. What is this black line? Is going to be torque developed by the motor. Okay, torque developed by the motor is more after this junction point, and the torque requirement of the load magnitude is less because this is torque, y-axis torque. Okay, meaning that after this junction point, what is happening? Torque developed by the motor, black, Tm, torque developed by the motor is more, torque requirement of the load is less. Okay, so my push is more from the motor side, but my load is unable to absorb that much torque, so remaining torque is going to be accelerating torque. Motor is developing more and load requirement is less, so developed one will become accelerating torque. So the moment it's acceleration torque, operating point will be unstable because it will accelerate, it cannot stop there. So B is going to be unstable. Always keep this particular point in mind. In the direction of increase in speed, you have to focus. Okay, if direction is reverse, direction of speed is reverse, under that condition B will become stable and A will become unstable. Always this particular point, keep it in mind. Okay, now let us think of very important equation. This has to be remembered because multiple times they will give questions from this area. Okay, now what is TD? Is going to be m by omega s into I2 square R2 by S. Okay, what is maximum torque? TEM or TDM? Maximum torque TM is going to be m by omega s into E2 square by 2x2. Okay, now slip at which maximum torque occurs? Okay, slip at which maximum torque occurs in this is R2 by S, here x2, E2, x2, R2 by S, right? So R2 by S magnitude should be equal to x2 magnitude, okay, such that maximum power will be absorbed to the R2 by S maximum power condition. So at maximum torque condition, R2 by SMT equal to x2, okay, or I can say that R2 equal to SMT into x2, just like that. Okay, now if I place in place of R2, for example here, okay, if I have R2 by S, what does it mean? R2 is nothing but SMT into x2, so SMT by S into x2, right? R2 value is going to be this and divided by S. Okay, so if you place these values here, you need not go for derivation. Actually it's a very small derivation only, because TD divided by TEM, m by omega s will get cancelled, E2 square will get cancelled, some kind of stuff. Ultimately TD divided by TEM is going to be 2 divided by SMT by S plus S by SMT will come. This has to be remembered. It's actually very easy to remember only, right? Now how questions come from this area will be like this. Okay, kind of they may give. Okay, for one of the induction motor, starting torque is maybe 150% of full load torque. Okay, and maybe pull out torque, maximum torque is going to be 5 times or 500%. Okay, of TFL, full load torque, and they can ask at slip at which maximum torque occurs. Okay, now what you are supposed to do, for example, in place of TD, if I write TST, okay, TST starting torque divided by pull out torque is going to be 2 divided by SMT, TM SMT by S is how much starting, 1 plus 1 by SMT is going to be TST by TEM. Okay, so this is going to be the case. Okay, now they have given TST 150% of TFL, TEM 500% of TFL. So if I divided by this, T starting by TEM is going to be 150% 1.5 by 5. Okay, TST of TFL, this TFL and TFL will be cancelled, 1.5 divided by 5 will come. Now you are going to use this equation saying that this is 1.5 by 5 equal to 2 divided by SMT by S. S is 1 plus 1 by SMT. So you can calculate SMT. Once you calculate SMT, how much will be the rotor speed at maximum torque condition is going to be NS into 1 minus S. They can ask this. Okay, slip at which maximum torque you can calculate from here. Okay, in this way questions will be asked. Let us see induction generator and speed control and braking also. Okay, one thing, without induction generator, speed control and braking we cannot discuss. Okay, and second thing is, if you observe your old gate questions, okay, most of the old gate questions might have come from our speed control, and in braking they did not give much questions in gate till now. Okay, and in induction generator also they did not give any problem till now, okay, but if you want to calculate induction generator problems, or if you want to calculate braking problems, you have to go through ESC descriptive problems. In ESC descriptive problems they have given already. Okay, but compulsorily I request you to go through induction generator problem of old IES descriptive and braking problems of old IES descriptive. I request you to follow. Okay, now basically before entering into induction generator, we should have a small introduction. Okay, if I have, for example, one element, what is in that I don't know. Okay, and here voltage is like this, current is like this. Okay, now this particular element, is it absorbing power or not? Most of the guys may feel that it is absorbing power. Yes, it will definitely absorb power provided these are DC components, but this may not absorb power if it is AC component. Okay, so the moment you are supplying sinusoidal voltage to any system, the moment sinusoidal currents are flowing here, okay, then I'll tell you one thing, position of current with respect to voltage only will decide. Of course, gradually you will understand. Okay, position of current with respect to voltage only will decide whether this particular property or this particular system is absorbing power or not. Now let us see. Okay, for example, if I think of this as a resistance, okay, this element is resistance, then what is going to happen? If you think of voltage like this, okay, phasors, and my current will be in line with it. Okay, now what is active power? Active power is going to be VI cos pi. Pi is the angle between voltage and current. The angle between voltage and current is 0, so this is going to be VI, which is actually absorbing this power, active power. Now if you think of reactive power, is going to be VI sin pi. Pi is going to be 0, so reactive power is going to be 0, meaning that this particular system is absorbing active power with 0 reactive power. Okay, this particular system is absorbing. Now let us think of, if it is not resistance, if it is resistance and inductance. Gradually you will understand, because compulsorily you have to understand this, otherwise your mind will not accept about induction generator. Okay, now let us see here. For example, this particular system is containing resistance and inductance. Okay, this particular system. Then what's going to happen? If I think of voltage like this, okay, current should lag behind voltage by less than 90 degrees. For example, current is like this. Okay, then what's going to happen? VI cos pi is having some value because this is I cos pi component, because voltage and current angle is pi. And if I think of this component is I sin pi. Okay, so I sin pi, V I sin pi value is there and V I cos pi value is there, so it is going to absorb P, active power, and it is going to absorb Q, reactive power. Okay, now let me think of one more system. Okay, one more system, that is resistance and capacitance, for example. Just few minutes, that's it. Okay, then if I think of voltage across this and current flowing through this. Okay, voltage across this, if I try to draw like this, my current would be leading voltage by less than 90 degrees. So just stay tuned, you'll understand. Okay, now the moment I is leading, Now Vi cos pi, this is going to be I cos pi value, and this is going to be I sin pi value. This is I sin pi value. Okay, then what's going to happen? Vi cos pi, absorbing power, active power, and Vi sin pi is going to deliver reactive power or absorbing negative reactive power. Okay, because already we got the standard, right? Inductance absorb positive reactive power, capacitance deliver positive reactive power. Okay, anyway, if you think of this, this particular system is going to absorb active power, and this particular system is going to deliver reactive power, or this particular system is going to absorb positive active power, and this particular system is going to absorb negative reactive power. Okay, now let us think of, I have one system, okay, kind of induction generator. In induction generator, for example, if voltage is like this, and if my current is lagging behind voltage by more than 90 degrees, meaning that our system is as usual. I'm not going to change current directions. Okay, I repeat, current direction should not be changed, meaning that voltage is like this only, current is entering into positive terminal of voltage only, but this particular current, okay, this particular current waveform is lagging behind with respect to voltage waveform by more than 90 degrees, which is going to happen in induction generator. Okay, then from network point of view, I'm trying to explain. Okay, then what is going to happen? Vi, this is going to be Vi sin pi value. Okay, and this is going to be Vi cos pi value, or I cos pi, I sin pi. Then Vi cos pi, if you think of, means I cos pi and voltage are means 180 degrees away, so it is going to deliver active power, or it is going to absorb negative active power, or it is going to deliver active power, and it is going to absorb Vi sin pi. Okay, so Vi sin pi, it is going to absorb active power. Okay, meaning that, means of course this particular thing I am going to connect to what do you say, induction generator very soon. Okay, in induction generator always remember one thing, that it is going to absorb reactive power and it is going to deliver active power. Why? My current waveform is lagging behind with respect to voltage waveform by more than 90 degrees, then Vi sin pi value is going to be in this direction only, lagging nature, so it is going to absorb reactive power, and Vi cos pi value is going to be negated or opposite direction or kind of 180 degrees away with respect to voltage, so it is going to deliver active power. Okay, now let us connect this to induction generator. Okay, if I connect this in induction generator, it means induction motor model will be like this. I hope most of the members know, or frankly transformer model. Okay, so same R1 X1, R0 X0, X2 dash, R2 dash we used to write in transformer, but anyway dash value we know, right? So these are actually X2 dash and R2 dash only. Okay, but dashes I'm not writing because we know already. Okay, how to transform from HV side to LV side or LV side to HV side. Okay, and X2 R2 bias means R2 bias will come. This is going to be induction machine structure. Now, if for example stator MMF is rotating with 3000 RPM. Okay, stator MMF is rotating with 3000 RPM. For example, rotor is at standstill. I strongly hold at the rotor not to rotate. Then what is going to happen? Because of starting torque, my rotor will be accelerated or will be tending to move towards 3000 RPM. Okay, so for example, my stator MMF is rotating with 3000. My rotor at standstill is getting the torque to rotate in the same direction in stator fed, of course. Okay, already I told you, if I don't say anything, it should be stator fed only. If it is rotor fed, intentionally we have to say. Okay, but anyway, like if stator MMF is rotating in this direction, my rotor also will rotate in the same direction, will try to rotate in the same direction. Okay, now if you leave that particular rotor, it would be accelerated towards reaching the 3000 RPM. For example, somehow if it is rotating with 3000 RPM, okay, stator MMF is rotating with 3000 RPM and rotor is also rotating with 3000 RPM, then how much is the slip? Slip is going to be 0. Okay, when slip is 0, how much will be the rotor induced voltage? S times C2 is the rotor induced voltage. Slip is going to be 0, rotor induced voltage is going to be 0. The moment rotor induced voltage are 0, rotor currents will be 0. Okay, when rotor currents are 0, rotor flux will be 0. Okay, now one thing let me tell you, in order to have a torque, stator should release some flux into the air gap, rotor should release some flux into the air gap. Interaction of these two fluxes in the air gap only will create torque. Okay, now stator is producing some flux to the air gap, but rotor is not getting an induced voltage. If at all, if rotor is rotating at synchronous speed, rotor will not get an induced voltage. So in the rotor you will not get any currents. So from the rotor, without currents, rotor flux will not come, only stator flux will be there, rotor flux will not come, so torque will not be produced. Okay, now by connecting some prime mover, if you are trying to rotate the rotor beyond synchronous speed, okay, maybe synchronous speed is 3000 rpm, if you are trying to rotate the rotor at 3500 rpm, means more than synchronous speed, then what will happen? Again torque will be produced depending upon the slipper, depending upon the relative velocity. We need not go that much depth. Okay, so the moment rotor is being rotated at 3500 rpm, then torque will be produced such that my rotor should try to operate at synchronous speed. Okay, meaning that, very simple, see here, stator MMF is rotating with 3000 rpm. Okay, rotor at standstill will try to rotate to 3000 rpm. For example, you release the rotor, my rotor is rotating at 3000 rpm. Okay, so up to this particular rotor reaching to 3000 rpm, my rotor will strive hard to reach 3000 rpm. Now, for example, if I am trying to rotate the rotor by external means, by connecting it to some prime mover beyond synchronous speed 3500 rpm, then again on the rotor some torque will be produced such that the torque will be trying to keep the rotor to synchronous speed. Okay, meaning that, for example, means stator MMF is rotating in this direction with 3000. Rotor, I am trying to rotate in the same direction with 3500. Then torque will be in opposite direction. Such that my rotor should try to rotate at 3000 rpm. Okay, then what will happen? I am trying to rotate to 3500 in this direction, but back torque is produced, so it is going to absorb some mechanical power kind of stuff. Leave about it. Okay, now the moment rotor is absorbing mechanical power, that absorbed mechanical power will come out as a electrical power. That's it. Okay, now point here is, if you try to calculate slip, slip is going to be ns minus nr by ns. The moment rotor speed is more than synchronous speed, now my slip value is going to become negative. Okay, now this is going to be the transformer kind of model will come. To induction motor also same model will come. Okay, now the moment slip is going to become negative. Okay, and one more thing is, of course, till now in GATE exam they did not give you how to convert the original thing into RTH XTH model, because if I want to convert this into RTH XTH model, that will become network theory. That's why means how to convert from here to here, till now they did not give question, and they are not going to give also. Okay, but in most of the questions they will give you these values. Okay, see here, in order to convert, because R2 by S and X2, rotor circuit is very important for in induction motor analysis. By keeping the rotor circuit as it is, you please convert this into Thevenin's model. Okay, so if you convert this into Thevenin's model, means open circuit voltage VTH will come, and across this, if you see into the circuit, RTH XTH has to be calculated. You are going to calculate. Nobody will give that particular question. Okay, because it's going to be Thevenin's model, Thevenin's finding Thevenin's equivalent in case of network theory. Okay, so the moment RTH XTH are given. Okay, and in GATE exam they can give you in two ways question. Okay, directly they may give you, means by neglecting shunt branch. Okay, they have given in that way only till now. Now the moment shunt branch is neglected, R1 will become RTH, X1 will become XTH, V1 will become VTH. Okay, otherwise independently VTH, RTH, XTH also they can give. Okay, in the question if they say shunt branch is neglected, okay, then RTH will become R1, XTH will become X1, V1 will become VTH. That's it. Now if I think of, see here, because in one of the publications they have given a mistake. Okay, we have to understand, and this type of question they have given in ES descriptive. Okay, now the moment slip is negative, okay, RTH XTH same model, means Thevenin's model of the original equivalent circuit. The moment slip is negative, okay, what's going to happen? It is a negative resistance. Okay, positive resistance will absorb positive active power, negative resistance will absorb negative active power, or it is going to deliver active power to the circuit. But at the same time, two inductances are there. So it has to absorb reactive power and it has to deliver active power. This particular question multiple times they asked, and we can expect the same question in upcoming gate exam also. Okay. Now in this way, if they ask you I2, okay, because rotor circuit is important, rotor circuit current is I2, meaning that here also current will be I2 only. Okay, everything is going to be same. Now if I try to calculate I2, is going to be VTH by, see here only they got the mistake, RTH minus R2 by S square, minus has to be added, plus XTH plus X2 square under root. Okay, now if you try to calculate PG, air gap power, is going to be number of phases into I2 square R2 by minus S, or this is going to be negative because it is going to deliver active power. Okay, now if you try to calculate TD, developed torque, okay, developed torque is going to be M by omega S into PG, right? We have seen in our previous sessions. Okay, now in this case it is going to be M by omega S into VTH square, because PG is going to be I2 square R2 by S divided by RTH minus R2 by S square plus XTH plus X2 square into R2 by S. R2 by minus S is going to be, torque developed is going to be negative, meaning that in opposite direction with respect to the direction of rotor. Okay, now if you try to derive torque equation, similarly previously we have done, right? Torque equation for motor and generator, if you see, okay, this is going to be, okay, speed of the rotor, 0 speed of the rotor, ns speed of the rotor, 2ns is the speed of the rotor. Okay, now this is going to be, see here, this is going to be torque developed in a motor mode. Okay, because from 0 rpm till ns, till it reach ns, it will behave like a motor, and after ns torque is going to be negated in the same way. Okay, if I try to convert this into slip, okay, slip is going to be 1 here, slip is going to be 0 here, and slip is going to be minus 1 here, okay, such that from here to here slip is going to be negated. Okay, now if you think of stable operating region, from here this is going to be stable, from here to here only stable. For example, induction motor is working under no load condition, okay, meaning that load is not there, you switch on the induction motor, some torque is there, and almost it will start rotating at the synchronous speed. Okay, induction motor at no load will start rotating at the synchronous speed, each is rotating here. Okay, and after that, for example, if you keep on increase the load torque, okay, okay, then what will happen? If you keep on increase the load torque will be increased. Okay, and in order to meet this torque at this speed, it is going to rotate. And if you increase the torque requirement of the load, my speed will be reduced and it will give this much torque. If you still increase the torque to maximum torque, okay, this is going to be the minimum speed. Now beyond this, basically this particular black line is the torque produced by the motor, okay, and red line is going to be torque requirement of the load. Now if torque requirement of the load is more than maximum torque that can be developed by the motor, okay, maximum torque that can be developed by the motor is here, okay, and this black line, and if your torque requirement is here, okay, if your torque requirement of the load is here, okay, that much torque my induction motor cannot produce. Then what is going to happen? Torque requirement of the load is more, but my motor is unable to produce that much torque, so my rotor is going to be stopped. Okay, so this is going to be the maximum torque. After that it is going to become unstable. So from no load to load, this is going to be the stable region. Okay, similarly in negative direction of the torque, this is positive direction of the torque, this is negative direction of the torque, from here to here only it will become stable. Okay, now that's fine. Now next thing is, this is going to be about induction motor. How to solve it? Same. Okay, if they give any stator things, Okay, so in this way you are going to consider. If they don't give any stator, if they give only rotor, it is going to be minus R2 by S square will become R2 by S square only, and this only X2 will be there, XTH will not be there, R2 by S minus S will be there. You are going to get the power. Okay, in this way we are going to solve the problems of induction generator. Now let us think of speed control. Okay, speed control basically is actually very easy topic, really easy topic. Okay, but what are the things has to be considered in solving the problem should be understood properly. Okay, now what are the speed here? Rotor speed is going to be ns into 1 minus s. Okay, and here so many methods will be there, but from so many methods problems cannot be formed. Okay, in what are the methods from which we can expect some problems, we are going to deal now. Okay, see here, ns is going to be 120 f by p into 1 minus s. Okay, now I can change slip. Questions can come such that rotor speed can be changed. I can change frequency. Questions can come, and I can change number of poles, but questions cannot come from here. Or cannot come, or problems cannot come, because our machines are not meant for equations calculations. Okay, our machines are meant for practical reality. Okay, in practical reality, poles cannot be changed that much easily, or kind of volume of copper requirement will be more, or kind of cost of the machines will be more, cost of the machine will be more, motor will be more. So normally we don't use this. Forget about it. Okay, or if you want to consider this, okay, for example, if I change poles, maybe from 2 poles to 4 poles I can change. Okay, so with 2 poles, how much is the synchronous speed? 120 f by p for a frequency of 50 Hz. It's going to be 3000 rpm. Now if I change number of poles from 2 to 4, how much will be the synchronous speed? It is going to 1500, 120 f by p, it's going to 1500 rpm. So from 3000 to 1500 I can reduce, but not in between. If I want to rotate the rotor at 2000 rpm, it is not possible. Okay, for time being, like kind of discrete speed control can be possible with number of pole change, and design like which will increase cost of the machine, and also normally questions cannot come from here. Now let us think of slip control. In slip control there are some methods. Voltage can be controlled, okay, rotor resistance control, can be controlled. All are easy only. Don't try to remember these nasty names, not required, because they are going to give in the problem, no. Okay, and slip power injection, okay. In slip power injection only one theoretical question can come, that is, in slip power injection method, frequency that should be supplied through rotor circuit should be the same frequency of the rotor circuit. Okay, so SF is the rotor circuit frequency, no. Normally if rotor is rotating at some slip. Okay, now with the same frequency we are supposed to supply input power. Okay, and beyond that, till now they did not give any question. They are not expected to give, because if they give you some phase control and all, okay, and with our online calci it is actually difficult. Okay, now these two will be there, and kind of frequency control will be there. We need not remember anything. Okay, whatever it may be, let us see how we are going to change the speed. Okay, now see here, as usual, same old discussion, only rotor circuit we are going to consider. Okay, R2 by S, this is X2 and this is E2, or we can say that by not considering rotor circuit, directly I can consider V1, meaning that complete stator circuit is neglected. R1 X1 is neglected, R0 X0 is neglected, only rotor circuit is being considered. Okay, now let us think of this as I2. Okay, how much is I2? V1 divided by R2 by S square plus X2 square under root. Okay, now how much is torque developed? Directly M by omega S into PG. Air gap power is how much? I2 square R2 by S. So this is going to be, though it is kind of repeated, just stay tuned, because multiple times we have to depend on this particular equation only, such that problems will be able to solve. Okay, now this is going to be V1 square divided by R2 by S square plus X2 square into R2 by S. Okay, I said clearly it should be divided into starting and running. Okay, independent of type of speed control. Actually, in speed control we are not going to learn anything new. Okay, now let me think of high slip region. High slip region in the sense it should be starting conditions, and let us think of low slip region. Low slip region in the sense running conditions. Okay, now in high slip region slip will be more. Okay, slip is more nearer to unity. At starting, how much is the slip? If I think of only at starting slip is going to be 1. When starting slip is going to be 1, okay, x2 x by r ratios will be always more in machines. So if I think of s equal to 1, this is going to be less, this is going to be more. So we are going to consider this equation. T starting directly is going to be m by omega s into v1 square by x2 square into r2, because s is going to be 1 no at starting. S is going to be 1 at starting. Now if I think of here low slip region, in low slip region slip is going to be less. If slip is going to be less, R2 by S is going to be more, so such that x2 you please neglect. So TD is going to be m by omega s into v1 square divided by R2 by S is going to be more compared to x2. R2 by S, x2 we are going to neglect. R2 by S square, R2 by S will get cancelled, so this is going to be R2 into S. Done. Okay, now only let us think of only these two equations, and don't remember these equations also, which is not required. Okay, a small circuit x2 r2 by s v1 or e2 has to be remembered, nothing more. Okay, now let us see here. Maybe if I think of voltage control. Okay, now voltage control in the sense, for example, if I think of rated voltage is 440 volts, for example, rated voltage, line voltage is 440. Now can I apply more than 440? No. If I apply more than 440, insulation failure will happen. Okay, so I am supposed to reduce the voltage, not increase the voltage. Okay, so if I reduce the voltage, for example, if voltage is reduced to 75%, okay, if voltage is reduced to 75% without actually touching anything, then what's going to happen? 75% square, 0.75 square, so starting torque is going to be reduced. Okay, for easy calculations, if I think of voltage is reduced by 50%, okay, starting torque will be reduced by 4 times or 1/4 of the previous starting torque. Now in that way questions can come. Okay, now next thing is, if I think of running conditions, okay, they will give you clearly whether means a constant torque requirement for the load or not, depending upon the load, because running conditions will be decided by the load, and starting and peak value means a pull out torque will be decided by machine. Starting torque will be decided by machine, pull out torque will be decided by machine, but running torque will be decided by load. Who are you to decide? Okay, now if I think of pull out torque also, for example, okay, pull out torque is going to be how much? M by omega s into v1 square by 2x2. Now if I think of, okay, let me draw voltage control. Okay, because with this it would be easy for you to remember, that's it. Okay, let me think of at rated voltage. At rated voltage characteristic is this. Okay, at rated voltage, how much will be SMT, slip at which maximum torque occurs, is going to be R2 by X2, or R2 by SMT. R2 by SMT should be equal to X2. Let me show you once such that you will remember. R2 by SMT, PG. Okay, this particular PG should be maximum in the sense R2 by SMT should be equal to X2. That's it. SMT is going to be R2 by X2. Okay, now if I think of voltage is reduced to half of the voltage, half of the rated voltage. Okay, questions can come from this area only. We are not going to remember anything which is not required. Okay, you need not remember this is voltage control, this is frequency control, this is rotor resistance control. You need not remember. In the question they will give no. Okay, now if it is half of the rated voltage, if I think of pull out torque and starting torque will be decided by machine. So pull out torque V1 is reduced to half, so Tm will be reduced to 1/4. Okay, now if I think of this as TEM pull out torque, and this says slip at which maximum torque occurs. Now blue. Okay, TM is going to be reduced to 1/4 of TM, 1/4 of previous TM. Question came in this area. Okay, now they asked one time, the voltage is reduced to 90% or reduced by 10%, my pull out torque will be reduced by how much percentage? They have given 19%, or in ABCD option they have given 20%. Now slip at which maximum torque occurs there, voltage is reduced, voltage term is not there, so slip at which maximum torque will not change. Okay, now if you think of starting torque will be decided by machine, voltage is reduced to half, so starting torque will be reduced by 1/4 of T starting, provided this particular black is T starting. Okay, so characteristic is going to be like this. Okay, because means the moment you reduce voltage or you change voltage, synchronous speed will not change, because 120 F by P is the synchronous speed. So if you change voltage, synchronous speed will not change, so synchronous speed did not change. Okay, now let us think of for a constant load torque. For a constant load torque. Okay, for a constant load torque, previously it was rotating. Okay, previously it was rotating at this slip, and now the moment you change the voltage, it is supposed to operate at this slip for constant torque load. Okay, now in running conditions, torque will be decided by the load, and pull out torque and starting torque will be decided by the machine. Keep this point in mind. Okay, now for example, if I think of here, this is going to be low slip region or running condition torque. For example, here in this case, for a given torque, okay, torque is going to be constant, decided by the load. Torque is going to be constant torque requirement load is there. The moment constant torque load is there, okay, voltage is reduced to half. Voltage M is not changed, omega S is not changed, R2 is not changed, voltage is reduced by half, meaning that slip has to be doubled such that same torque will come now. So my S2 is going to be 2 times S1. Okay, for example, voltage is reduced by 10%. Okay, in order to produce the same torque, voltage is reduced by 10% or 0.9 square. 0.9 square inverse is going to be new slip. As per the new slip, you are going to get the new speed. That's it. Okay, so this is going to be about the voltage control. Okay, now I don't want to repeat redraw the same. I'm going to use the same equations, but let me draw for the other things. That's it. Okay, now let us think of equations are same. Okay, now let us think of maybe rotor resistance control. In the exam they are going to give you when rotor resistance is doubled, how much will be the variation of starting torque, or how much will be the variation of pull out torque or peak torque, or in order to maintain the same torque, at what new speed it is going to rotate if a rotor resistance is doubled. Such a kind of question they are going to ask. Okay, now maybe rotor resistance if I try to change. Okay, so with rotor resistance of R2, let me draw the characteristic. Okay, so this is going to be TEM pull out torque, and this is going to be slip at which maximum torque. Okay, this is going to be the characteristics for rotor resistance control. Okay, now in the second case, if rotor resistance is doubled, means what is going to happen? Okay, now let us think of pull out torque. Pull out torque, is it going to change or not? No change, because m by omega s is there, v1 square by 2x2 is there. Previously v1 was variable, but now in rotor resistance method v1 is going to be same. Rotor resistance we are going to change, rotor resistance term is not there, so TEM will not be changed. If you change rotor resistance, pull out torque is not going to change. Okay, you need not remember any conclusion, directly go to the exam and remember that particular small diagram x2 R2 by S v1 and write equations there. Okay, now let us think of slip at which maximum torque occurs. Now R2 is doubled. So slip at which maximum torque occurs will be doubled. This is going to be SMT2 and previous one is going to be SMT1. Slip is doubled. Okay, for the pull out torque. Now next thing is, let us think of starting torque. Okay, because starting torque and pull out torque will be decided by machine. So for example, R2 is doubled. Okay, remaining everything is constant, R2 is doubled, then starting torque is going to be doubled. Okay, so previously this is starting torque for the black, now this is going to be 2 times TST. 2 times TST. Now draw the characteristics. Now let us think of for given torque requirement of the load. Okay, for given torque requirement of the load. For given torque requirement of the load, because if the moment you find slip, rotor speed you can find. Because ns into 1 minus s. So this is S1 for a given torque requirement, and this is S2. This is S2. S1 to S2 change has happened or not? Yes. The moment slip is changed, automatically rotor speed is going to be changed. Okay. Now let us think of for given torque requirement of the load. For given torque requirement of the load in the running conditions. Okay. So for a given torque requirement, if torque requirement of the load is constant, under that conditions, if rotor resistance is doubled, slip is going to be doubled. Getting my point, right? If rotor resistance is increased by 10%, slip is going to be increased by 10% because remaining are going to be constant. The moment you calculate the slip, problem is solved, because slip is the only independent variable in induction machine. Okay. Now, this is going to be kind of how to solve problems with rotor resistance method. Okay. Now, forget about it. Now, let us think of voltage frequency control. Okay, frequency control a bit tricky. Okay, but same equations will not change, same equations. Okay, now let us think of frequency control. In frequency control, one small logic you have to keep it in mind. Okay, because if you vary frequency, synchronous speed is going to be changed. If synchronous speed is changed, automatically rotor speed will have to be changed. Okay, now the thing here is V by F ratio. Okay, for example, if rated, okay, let me write here, rated voltage is 440 volts line to line and rated frequency is 50 Hz, for example. Okay, now operating flux in our machine directly proportional to V by F, we know. Okay, now for example, if I am reducing frequency to 25 Hz, the moment I reduce frequency to 25 Hz, okay, if I maintain same rated voltage, for example, so 440 volts at 25 Hz, so frequency is half, so operating flux is going to be doubled, which will lead to saturation of machine and some kind of stuff, forget about it. Okay, so in order to avoid my machine not to enter into kind of non-linearity, so the moment frequency is reduced to half, if voltage also is reduced to half, then V is reduced to half, frequency is reduced to half, operating flux is going to be same operating point, it is going to be state. Okay, now for frequency less than rated frequency, voltage also will be reduced in the same proportion such that operating flux will be maintained constant. Okay, now if you want to increase frequency, okay, in order to increase the speed, if you want to increase frequency to 100 Hz, the moment you are trying to increase the frequency to 100 Hz, okay, then in order to maintain V by F ratio constant, voltage also should be doubled. If you increase the voltage to 880 volts, insulation failure will happen. Okay, because rated voltage, one thing I'll tell you, depending upon voltage, some insulation design is there, depending upon current, conductor design is there, depending upon frequency, only iron thing will be there. Okay, now for example, if you increase frequency to rated or more than rated, if you increase frequency to more than rated, under that condition more than rated voltage cannot be maintained, frequency can be increased. If frequency is increased for rated voltage, operating flux is going to be reduced. Okay, so if you reduce operating flux, it is going to be fine, but it should not be more than rated operating flux. Okay, now see here, in this two conditions will be there, two conditions. Okay, if your frequency is less than rated frequency, okay, under that conditions V by F ratio can be maintained constant. Okay, or V is directly proportional to frequency. Okay, if your frequency is more than rated frequency, V by F ratio cannot be maintained constant, so V is going to be at V rated only, so frequency only you are going to increase. Frequency only you are going to increase. Okay, or we can say that this has subsynchronous speeds. Terms doesn't matter, frankly. This is super synchronous speeds, beyond synchronous speed. Okay, just keep this point in mind. Remaining we will be able to do. Equations are same equations again. Okay, with the same equations, see here. So I'm trying to do at frequency less than rated frequency such that V by F ratio will be maintained constant. Okay, so frequency is less than rated frequency, our voltage by frequency is going to be constant, subsynchronous speeds, or we can say voltage is directly proportional to frequency, right? Okay, now see here, if you think of starting torque, okay, because starting torque and pull out torque will have to be maintained by the machine, it will be decided by the machine, but operating torque will be decided by the load. Okay, now see here, let us think of starting torque is going to be how much? M by, or constant only, no, M is going to be constant only, so 1 directly proportional to 1 divided by omega s, 2 pi f, or omega directly proportional to frequency, right? So frequency into V1 square. V is directly proportional to frequency, V is directly proportional to frequency, so this is going to frequency square divided by x2 will be decided by frequency or not? Yes, frequency square into R2 is going to be constant. Rotor resistance we are not going to vary in this case, only frequency and voltage we are varying such that V by F ratio is constant. Okay, now let me think of at rated voltage, rated frequency. At rated voltage and at rated frequency, if you try to draw the characteristics, okay, rated voltage, rated frequency, okay, this is V rated, F rated, V rated and F rated. We got this as a starting torque, we got this as a slip at which maximum torque occurs, and we got this as a pull out torque. Okay, now if I try to reduce voltage by half and frequency by half, okay, frequency, of course this half and all they will give in the exam. Okay, voltage is reduced by 10% such that V by F ratio is maintained constant. What will happen to starting torque? What will happen to pull out torque? What is the operating condition? At what speed it is going to maintain in order to set up or in order to provide the same load torque in the running conditions, they will ask. Okay, now see here, the moment starting torque, okay, starting torque, see here, frequency square and inversely proportional to frequency. So if frequency is half, my starting torque is going to be doubled, 2 times TST. Okay, now let us think of pull out torque. Okay, so pull out torque, if I think of TEM directly proportional to number of phases we are not going to change, 1 by F into V1 square directly proportional to frequency, V is directly proportional to frequency, and 2x2 F. Okay, so is going to be constant. So in V by F control, or in variable frequency control, if you provide the variation in the voltage also, TM is not going to change. Is going to be same. Now if you think of slip at which maximum torque occurs, okay, slip at which maximum torque occurs is going to be R2 by X2. The moment frequency is reduced, okay, slip at which maximum torque is going to be doubles. Okay, now what's going to happen if you think of, see here, new characteristic, previously it was 0 speed NR, this is going to be NS. Now what is NS? NS is going to be 120 F by P. Now the moment frequency is reduced to half, my NS is going to be reduced to half, NS by 2, synchronous speed. Okay, now pull out torque is going to be same. Okay, now the characteristic is going to be, pull out torque is going to be same, starting torque is going to be increased. Now if you try to have same torque requirement, Okay, in order to have same torque, because in running conditions, because starting they can ask and pull out torque they can ask, and in running conditions, in order to have the same load torque requirement, at what slip it is going to rotate can be asked. Okay, now see here, in order to have the same torque requirement, see here, where is the running condition? Running condition is here. Okay, in order to maintain the same torque requirement, let me think of directly proportional to m is constant, directly proportional frequency square divided by R2 constant into slip. Okay, so this is directly proportional to SF. Okay, S into F. That's why we say in order to maintain the constant torque requirement of the load, slip frequency should be constant. Frequency is directly proportional to NS only, no? Or directly SNS should be constant. SNS should be constant. Okay, of course, one time old gate question came here, and yeah, we'll see that old gate question now. Okay, type of. Now, slip frequency should be constant or slip speed should be constant. For example, see here, in order to maintain the constant torque, requirement of the load, okay, if frequency is reduced to half, okay, such that my slip frequency should be constant. For example, maybe at starting when you supply 50 H, okay, to two pole everything, my rotor is rotating with 2700 RPM. Okay, now when you supply 25 H, at what speed it is going to rotate? Okay, so in the first section, what is slip speed? Slip times synchronous speed is going to be 300 RPM, no? 300 RPM, no? Okay, in the first case, how much is synchronous speed? Synchronous speed is going to 50 H 2 pole, 3000 RPM. 3000 RPM. Now the moment I provide 25 H, what is the synchronous speed? Is going to 1500 RPM. In between here to here, slip speed should be maintained constant. So in the second case, it has to rotate 1500 minus 300 is going to be 1200 RPM. It will rotate at 1200 RPM. Okay, because in order to maintain constant torque requirement of the load, slip frequency or slip speed should be constant. You understand my point? The moment you provide V by F ratio as constant. Okay, so this is going to be the case. Okay, one time they asked one question. Let me tell you that question. Okay, see here, stator they have given and rotor they have given. Okay, I think they have given here maybe some 440 volts for example. Okay, per phase, or maybe let me think of 200 volts at 50 H. Okay, this is 1 ohm, this is J2 ohm, and this is J2 ohm. Okay, just like that. This is going to be R2 by S, no? This is going to be 1 by S. Okay, and they asked one question in such a way that means the moment if I reduce frequency by maintaining V by F ratio constant, see here, the moment I reduce frequency, starting torque is going to be increased or not? Yes. So at starting torque of rated voltage, rated frequency is this. If I reduce voltage to half and if I reduce frequency to half, starting torque is increased. Now they are asking a question. Such that by what percentage of frequency should be reduced, or how much should be the supply frequency such that starting torque should be maximum torque. Okay. So starting torque is reduced. Starting torque from black to blue increased. Blue to red it should be increased such that starting torque should be equal to pull out torque. How much should be the frequency that should be supplied, or how much should be the voltage that should be supplied? They asked the question. Now see here, very simple. Though it look a bit difficult, basically it is very easy. Okay, now if I think of pull out torque condition, okay, what is the pull out torque condition here? Pull out torque condition is going to be R2 by SMT, because this is PG, should be equal to magnitude of this, no? So we can write 1 by SMT should be equal to under root of 1 square plus 2 plus 2, 4 square. So this is going to be under root of 17. Okay, so how much should be slip at which maximum torque occurs is going to be 1 by under root of 17, no? 1 by under root of 17, no? Now means see here, frequency has to be reduced and voltage by V by F ratio should be maintained, meaning that voltage also should be reduced in the same proportion, and how much should be the operating frequency such that starting torque only should be the maximum torque. Okay, now what was the condition we got? Slip frequency should be constant. Okay, so in order to maintain the same torque, because here at SMT you are going to get the pull-out torque. In order to have the same pull-out torque at starting, how much should be the frequency they are asking? Okay, so slip, in order to maintain the same pull-out torque, slip frequency should be constant, right? So S1 F1 should be equal to S2 F2. S1 is how much? 1 by root 17 into frequency is going to be how much in the first case? 50 Hz. 50 Hz equal to S2 is how much in the second case? They want to have maximum pull-out torque at starting only. 1 into what is the frequency in the second case? We have to find. So how much is frequency here? Frequency should be equal to 50 by root 17. Or if you want voltage also, in the same ratio voltage also should be reduced such that 200 divided by under root of 17 is going to be the question. Okay, now let us think of same equations are same. Okay, of course you may have to practice. Okay, without practice, just by seeing the content you will not get anything. Okay, definitely you may have to practice. Now if the when V by F ratio cannot be maintained, or when operating frequencies are more than rated frequencies, because already we discussed, right? Means voltage cannot be increased but frequency can be increased. Okay, if frequencies, operating frequencies are more than rated frequencies, then we cannot maintain V by F ratio constant because voltage should be more than rated. Okay, now coming to the point, when frequency should be more than rated frequency, meaning that voltage is going to be constant at rated voltage. Okay, frequency is going to be varied, super synchronous speed. Again, same old story, starting torque, pull-out torque should be decided by the machine, and running torque, in order to have the same running torque, at what speed it is going to rotate is the point of interest. Okay, now frequency should be more than F rated. Now see here, starting torque directly proportional to M1 divided by omega S frequency into voltage now is going to be constant, 1 divided by x2 square frequency square into R2 is constant, so directly proportional 1 by F cube. Okay, now if you think of pull-out torque is going to be M directly proportional 1 by omega S, voltage is constant now, divided by 2 is constant frequency, so inversely proportional frequency square. Okay, now remaining things automatically will fall. Now first of all, try to draw the characteristic. If we try to draw the characteristic, automatically we will be able to understand. Okay, at rated voltage, rated frequency, at VR and FR, if we try to draw the characteristic, this is TEM, pull-out torque, this is going to be starting torque. Okay, after TEM, this is going to be running torque. That will be decided by the load. Okay, now this is going to be NS. Now, if I think of my frequency has to be increased more than rated frequency, voltage should be same, meaning that at rated voltage and 2 times rated frequency. 2 times rated frequency in the sense my synchronous speed is going to be 2 times NS. 2 times NS. Okay, now let us see here, pull-out torque inversely proportional frequency square, frequency is doubled, so my TM should be reduced by TM by 4, right? And starting torque inversely proportional F cube, frequency is doubled, so starting torque should be TST by 8. That's it. Now remaining characteristic. Now in order to maintain the same torque requirement of the load, what is the condition has to be understood. That's it. Now in order to do that, we have running conditions here. Okay, now see here, in order to maintain the same torque requirement of the load, Okay, in order to maintain the same torque required of the load, see here, directly proportional to 1 divided by F into 1 divided by R21 into S. So directly proportional S by F. If frequency is doubled, in order to maintain the same torque requirement of the load, if frequency is doubled, automatically slip also should be doubled. As per that, slip can be calculated. As per that, rotor speed can be calculated. That's it. This is all about speed control.